Okay, a couple things I want to mention to you, and that is when you come to class, always sit in the first 7 main rows. So, young lady in the black, no, don't look over there, look at me. Okay, raise your hand. High, really high, like you're reaching the seat. Okay, that girl over, that young lady over there, she's in the last row that you're allowed to sit. Okay, and if you're sitting behind her row, then I deputize people to come back and body slam you and move you to the front. Okay, so well, we'll dispatch with the body slam, but move you to the front. So, and it just keeps things a little more manageable, so that my voice doesn't get too overused and stuff like that. A couple things I want to mention. The homework 1 from last week, which was due Friday. Raise your hand if you added Friday and didn't get a chance to do it until. Okay, there's a couple of you in here. I'm gonna extend that a couple days, and so you know what they basically do for that federal attendance regulation. They get the system administrators in web courses to run a program, and it basically looks at every course of every student and checks every course of every student for clicks. So if you're clicking on homework, ding, that means you're on board and you're participating. So it's pretty limited. It's pretty easy to do, but I understand that some students that got in late on Friday didn't get a chance to actually get in web courses until Saturday. So we'll get you guys. So hopefully they'll have gotten some clicking from you on Saturday, if not Friday. Questions about that, Jazz? Okay. And I see everybody's bundled up, scarves and winter coats and stuff. I came to school in a t-shirt this morning. So, because I'm from up north, I'm not like you guys from Florida. Uh, but in the summer, oh man, I feel like it's just the opposite. I'm suffering. Well, I'm originally from New Jersey, and I spent a lot of time out in Montana, up northern New Jersey, Morris County. Morris County. Right. Yeah, down by the beach. Yeah. All right. Here's our quote of the day. In questions of science, the authority of 1,000 is not worth the humble reasoning of a single individual. And that is something that Galileo said during his times of storm and strife with his fellow academics, who at the time were slavishly devoted to whatever Aristotle said. They didn't bother to make any measurements like we're doing and like what we have done, observations, no. What if they just were, kind of like moles, underground. They never got to see the light of day. They just went by whatever Aristotle said. And Galileo liked Aristotle, but he didn't like the fact that people wouldn't even look through. Some people wouldn't even look through his telescope. When he pointed out, look at this is the Milky Way up there. It's not just some blob in the sky. Those are actual stars. The moon, the surface of the moon, the mountains of the moon that he discovered. A lot of people wouldn't even look at it. SI schedule to be announced hopefully this week. No word yet, Shy? Okay, so hopefully by Thursday we'll have something. And that will be posted here every day, and we'll go through this slide, something like this every day. Now, I would like to go over some of the tools that we have this semester, specifically the electronic textbook. And as I mentioned last week, the electronic textbook is slightly more economical if you buy it directly from kendallhunt.com/Brickner. But if you buy it from the bookstore, you get one of those little code cards. It's a little bit more expensive. Well, a lot more expensive. Anybody get it from the publisher? Do you? Okay, raise your hand if you got it from the publisher and they didn't have to mail you anything. Okay, you just got it. So young lady with the aqua sweat hoodie, yeah, that'd be you. Yeah. Uh, so you use your debit card online, right? Wait a minute. First, what's your name? Rebecca. So Rebecca, you used your debit card online, and then 5 minutes later you were looking at the text, right? Yeah, you got to sign up and then get the Bookshelf app. We're going to talk about that Bookshelf app right now. It's kind of nice. Here's the front cover of the textbook if you haven't gotten it. And when you operate the Bookshelf software, forward please. When you operate the Bookshelf software, this is what it looks like. Here's a close-up of the book itself, Interactions, Introduction to Physical Science, written by me, half of it by me. And when you click on it right here, it pops you directly into the book itself. And it changes the left-hand menu bar, and you start getting chapters. It'll pop you, I believe it pops you back to the last place that you were reading. Okay, and there's over here on the left side is a set of collapsible menus and stuff that are pretty easy to navigate. And let's take a look at those chapters and stuff. This is what chapter 1 looks like. So you click in there. Here's chapter 1, and you can expand it. Make it bigger and stuff like that. Here's the introduction. First page of the introduction. And the chapters, you can see down here, different chapters. Each of these chapters expands when you click the chapter. So here's 1.2, I believe that is. And here's the zoom effect. It looks a little bit like this. And so you can read it a little bit more easily. You can actually copy and paste as well. There are highlights in the textbook as well. So this whole issue of highlights, or highlighters I think they call them, is a way for you to make notes of whatever your heart's desires. It's like putting little sticky notes in a regular textbook. And the notes actually look like, this one looks like a pink sticky note. All right, so let's take a look at what those highlighters look like. Okay, so here's some stuff being highlighted. Wow, that's supposed to look pink. It actually looks kind of brown on this computer screen. It'll look pink in YouTube. Okay, so there's your highlighter. And if you click on this little blurb over here, this little yellow sticky note icon, that will pop out the actual text that I typed in. Oh, did I say that these are my highlights? Yes. Are my highlights valuable to you as a student? Yes. The other thing that you can do is head over here to the highlights sidebar, and then you click on that, and it drops down a list of all the highlights in the book. And you can scroll up and down the list. If you click on it, it'll pop out the actual text that I typed in. And what I typed in, this is the basic question for a lot of scientists, like all those PhDs down in Houston who work for NASA. And what I was talking about was what will be the future state of the things that a scientist sees. And that's actually a huge theme for this entire course. Now, one of the nice things about these notes is that you can copy and paste. So, for instance, here's your note that you've popped out. And if you then cut and paste into some other file, like you're working on my notes, January 9th, 16.txt, or whatever file that you have, you can copy my notes into your text file or word processing file, whatever you want. And you can have that and do whatever you want with it, which is Kind of nice. Uh, so definitely use those highlights. And the way that you can see my highlights is by subscribing to them. Now, how do you subscribe to them? Well, basically what you do is you use my email address, which is right here, and I want you to write it down. Uh, Let me make it a little bit bigger for you. It's my phony Knight's Mail email address. And I can't remember exactly where it is you subscribe. Do you remember, Dare?
In the bottom left-hand corner, there's a little like plus sign and then a little person.
Okay. So in the bottom left, there's a little plus sign and a person that you click on, and then you can enter my email address. Here it is in big letters. And notice that it's misspelled, and that is deliberate. So, Brubeckner. I have one of these last names, a German last name that's infinitely mispronounceable. And in the old days, when I was a kid, we didn't have cell phones and unlimited talk and text and all that. So when when I was in college, I would have to call my dad, collect. Which, for those of you that don't know what that is, you talk to the operator, and you say, I want to make a collect call to, and you give them the phone number, and then they call that number. And they get the other person on the line, and they say, do you want to accept a collect call? And the billing goes to the person that you're calling instead of. So if you're at a phone booth is like this box with glass sides where there's a little phone in there, and you put coins in it, and it operates. You actually have to press these buttons and stuff. And if you're calling your dad long distance from Minnesota to New Jersey, which I sometimes had to do from a phone, I had to pay, you have to feed quarters into it like crazy for 3 minutes. And so anyways, my dad, collect calls, used to have to do that. And so I heard my last name mispronounced about 9 million times, this being one of them. So it's, because you'd always have to say, I'm calling, and my name is Thomas Brickner. And man, they would mispronounce it like crazy. Now, don't send me any email to this address because I won't answer it. I don't even look at it. I mean, I have it just to see. I got it just so I could see what your guys' email was like, but I don't really ever use it. I might even have some email in there. I have no idea. But do use it to subscribe to my highlights, and then you'll be happy you did, because number one, I wrote this book. Second, these are my notes on the book that I wrote with you guys in mind. And so I wrote it with you guys in mind. And the notes I make are knowing that you guys can subscribe to them. So I'm not going to put any little notes in there about, something private or anything like that, or something stupid, or off topic like the Green Bay Packers or something. But it's all going to be about class and stuff, and what might be on the first midterm. Did I say you might find a tip on what's going to be on the midterm? Yes, I did say that. And so it's going to be valuable for you to look at those highlights and maybe get a head start on the midterm. Now, the other thing is the midterm itself, exams in themselves, if you think about it, they're my way of checking your brain to see if you savvy the things that I think are important. Okay? Now, physics is this enormous topic, and I can't cover everything. I mean, if we had some other textbook, with 400 pages, and even this textbook, I can't cover every single topic on every single page. So every day I have to make a decision, what's the most important thing to cover? And then that's what I talk about in lecture. Like today we're going to be talking about velocity and acceleration. And so when I talk about something in lecture, it's important. And I'm necessarily bypassing maybe a few things that I judge are less important. So on exam day, I'm trying to see if you savvy that stuff that we talk about in lecture. All right. So really, these highlights are nice because it shows you one more way to understand the things that I consider important. And then if you can, talk with your neighbor, talk with your study partner about the same stuff and kind of get, triangulate in on it accurately, you'll do better on the exams, which is what you want to do. Because on the exams, the more you can think about these topics, not just regurgitate stuff you've memorized. Anybody can do that. Any engineering student can do that, and that's no great shakes. But thinking, that's much more difficult, and that's your task on exams. Once you get past the basic stuff. So here's your study tools list. Definitely try to use those to your heart's content, and see how it goes. Now, does anybody have a question about getting into the textbook? Okay, Alexis.
Yeah, I was just wondering if do they have paper copies of this?
The question was, do they have paper copies? And the answer is no.
Right.
I only publish it as an ebook. So if somebody emailed me or messaged me in web courses last week, Dr. B, what about this print version? And I don't know if it's a scam or not, but we didn't publish a hardcover, soft cover, or any cover, loose leaf or anything. Just the ebook. That's the only thing published. So if somebody's trying to sell you something like that, it's illegal. It's a scam. All right. Another question. Yes. The question was, is there any place where we can find a cheaper version? And the answer to that is yes, the publisher's website is cheaper than the bookstore. Is that what it's the bookstore. You mean at the bookstore? At the UCF bookstore? At the UCF bookstore? Well, see, all right, it's kind of hard to tell, but what I have heard in the past is that the UCF bookstore sells it for a lot more than what you get directly from the publisher. I can't remember your name back there. Laura. No. Rebecca. Okay, Rebecca. Do you mind if I ask how much you paid at the website? 85? 85 is what they told me, what the publisher representative told me would be the price at their site. And they've jacked it by, I don't know, $30 or something over at the bookstore. So buyer beware, caveat emptor.
I'm pretty sure the UCF bookstore matches the price.
The UCF bookstore matches the price. I will not hold my breath about the bookstore. Okay. When I see that, I'll believe it. Question. You can get by without a textbook. You can get by without coming to class. You can get by without homework. You can get by without anything. Everything is optional, my friend. And so it's up to you. You make. I know, and you make the call. What you think is important. Now, if you want to share it with somebody, you can do that. But I wrote the book deliberately and specifically for this course. So that's my view of it. And whether you want to get it or rent it or what have you, that's your decision. And I don't claim to make any. I don't make any claim on your money. Okay. And if it were up to me, I'd publish this same book for $10, not 85. And then I could say, yeah, go ahead and get it. $10. Everybody can afford $10. 85 is a lot more. Financial aid is a pain in the neck. It's sometimes slow, so you got to make the call. Just like everything else. Another question. Okay, let's keep going. Our main topic for today is figuring out motion. Now, I'm starting in and actually talking about stuff from chapter 1, section 6. So I'm assuming that everybody has read the introduction and at least up to chapter 1.5. If you have, or 1-5, if you haven't done that, I'll go ahead and do that. It's basically a little blurb, couple little pages about what a meter is, what a second is, and what a kilogram is, how we've set up the metric system for those three specific units of measurement. They are the basic measurements for a good portion of the semester. There are other metric measurements like electronic or electric current and temperature stuff, but for the basics of motion, these are what we need. So we're starting today with the velocity concepts. We'll try to get as far as we can and get to acceleration concepts by the end of the lecture today. And this basically follows Sir Isaac Newton's admonition in the quote here at the beginning of chapter 1. For all the difficulty of philosophy, in other words, physics, seems to consist in this: from the phenomena of motions to investigate the forces of nature, and then from these forces to demonstrate other phenomena. And that is his program. So what we're going to do is try to get a handle of motion, then figure out forces, and then figure out other phenomena. Now, by other phenomena, I mean molecules, periodic table, and quantum physics. Okay, and so the main thing is to get a handle on the initial condition of a moving object and then predict its future position and its velocity at a future time. Now, to do that, you have to know how to measure the quantity of matter in kilograms, the time and position using a clock and using a meter stick. Then you have to get a velocity, and then finally an acceleration. And the laws of physics are written in terms of accelerations. Sir Isaac Newton's 3 laws of motion are really laws concerning acceleration. And the input information for his laws of motion are initial position and initial velocity. So those are what we're going to tackle first today, is velocity and acceleration. And positions I'm going to assume you know the basics of. So let's go ahead and get to that. And you'll note here in this tilted paragraph with 4 different sublists, or 4 items in the sublist, there's a note, page 4. Okay, that's from the textbook. And I'll try to add that into the notes when I pull something directly or make some reference to where you should be or where you should have read in the textbook, just so you kind of orient yourself to the ebook that we're using to help us with this study. So let's go ahead and tackle this main concept. Oh, and you know, before we do that, I want to invite the 2 students, the 2 young ladies over here on the right side of the room. Could you come up to the front with your skateboards? We are going to do a demonstration today. It's just going to be 2 students operating their skateboards. And if you guys can. All right, can you come up here to the front? And first of all, I need to know your names. Jordan. Caitlin. Jordan and Caitlin. Jordan and Caitlin, what I would like, you're Jordan, right? Okay, Jordan, I want you to go to the top of this aisle. Caitlin, I want you to go to the top of that aisle, please. And what you're going to do is mount up on your skateboards and just slide down here to the front of the room. And what we're all going to do, the rest of us, are observe what they're doing. All right, so just observe what they're doing. And just mount up. Okay, Caitlin, ready? Okay, shove off and la 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 la. Okay, great. Jordan. No, 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 no. Yay. Sweet. All right. Question. Jordan and Caitlin, what happened to their speed as they came down the aisle? What do you think the speed increased? Did it look like they were going faster by the time all right, switch sides and do it one more time. Let's re-verify that. Okay? Just so that there's no tricks. I always try to, verify. Trust but verify. All right? And Jordan and Caitlin, try not to fall and break your arm or anything like that. Hopefully this is good. Okay, Jordan, ready? Okay, now watch her speed. Go ahead. And then she slowed down. Caitlin, go ahead. Faster down here? Write it down in your notes. Caitlin and Jordan are faster at the bottom than they were at the middle. And they were 0 up at the top. Okay, thanks, you guys. And let's give them a hand. Jordan and Caitlin. And Caitlin, how do you spell your name? C-A?
No, K-A-T-L-Y-N.
K-A?
Catlin.
Caitlin? Okay.
Yeah.
Kind of like Katniss Everdeen. Okay, good. Thanks, Caitlin. And Jordan, thank you. All right, so to predict the future state of the skateboarder, we need to, the future state of anything, like a spaceship that you're trying to launch from Cape Kennedy Space Center. You need to have the initial state or the most recent state available in terms of position and velocity. So the position is basically a set of 3 numbers, usually if you're thinking in 3 dimensions, and a direction from the origin. Or it could be a single number and a direction from the origin. 3 numbers relative to the origin, or a direction from the origin and a distance. Either way, you encode the position that way. So 3 numbers would be like the x-coordinate side to side, and the y-coordinate up and down, graph paper-wise, and then the z-coordinate toward or away from you. And direction is a function of that. Velocity encodes the speed and the direction. So they had the same basic direction, kind of slanting downward at a tilt, Jordan and Caitlin both, but the direction of their velocity was the same, but the magnitude of their velocity, their speed, was different. And so speed and direction are both part of the velocity concept. So when I say a velocity, what I'm really talking about is some measure of how many meters per second you're moving and a direction, something toward which you are moving. And usually it's relative to the origin of coordinates. Like if you're in a ship at sea, a lot of times it'll be relative bearing, relative to your ship. But if it's mission control, it's how many meters you are from the launch at Kennedy Space Center or wherever it's launching. Okay, and so that there's a little bit of variation that, with that. So that's the first thing the initial conditions, the initial position, the initial velocity. Then the other thing is some way at which those things change over time. And what Sir Isaac Newton figured out was under most forces, most changing physical systems in the universe The only thing you really need to know is accelerations. And so he encoded that in something called an equation of motion. How does the motion change? In other words, how quickly are they speeding up? Do they get another meter per second of speed for every half second, for every quarter second, for every 2 seconds? How quickly do they acquire speed? That's the whole thing about acceleration. And if you know that, and your initial position and your initial velocity, you got it all. Okay, and so that is why that is our objective, to get a hold of some equation of motion along with our position and velocity information. Now let's get a little bit more information about position and velocity. Some notation, some vocabulary. Position is a vector. Distance is a scalar. A vector is something that has a direction and a length, like an arrow. Okay? And distance is a number. If I say that I'm 2 miles away from you, and that's all I tell you, you could be anywhere on a circle of radius 2 miles, north, south, or anywhere in between. But if I tell you the direction, then you know exactly where I am. 2 miles and northwest of classroom building 2, you know exactly where I'm going to be. You'll be able to send your drone over there, hover overhead, and take a photo of me, okay, for posterity. Distance is computed as a regular number between 2 positions, and it uses Pythagorean theorem. And Pythagorean theorem actually works in 3 dimensions. It would be a squared plus b squared plus, some third something, like the z distance quantity squared, and that would be the distance squared. But this is a good old Pythagorean theorem. We're not going to get much fancier than that trigonometry-wise. Velocity is also a vector, as I have mentioned, and speed is a scalar. Speed is a computed quantity. It's not a measured quantity. We don't really measure speed. There's ways to measure speed. For instance, a police officer can time you on the road, but he's, if he's timing you between 2 mileposts, then he's basically just using timing. But if he has a radar gun, he's using the radar technology to figure out your speed. But most of the time it's not a measurement, and it's computed from a ratio of distance and time. So direction of position and velocity, they use a little bit of trig. We're not going to do a huge amount of trig, if any. Basically just Pythagorean theorem, which is what this little kitty cat is looking at, as well as those pancakes. Which, and just so you know, sometimes if I don't like to just have blank notes, endless text, So I'll jazz something up with a picture from reddit.com. And this was, I don't know, a couple months ago on reddit.com, some kitty cat. Anyway, so vectors and scalars. A scalar means just a regular number that doesn't have a direction. And it may be related to a vector, like speed, like distance, but it is not a vector. Now, I want to make some calculations of velocity with you. And would you guys like to dismiss early today? I think we're going to be a little bit early today, but, oh, and by the way, get your clickers out if you have them. And you're going to, for those of you that have registered your iClicker, you'll be able to get another bonus point today. Question? My astronomy? You're in both of my classes? Oh. Register it again. Oh, does you? Okay, good. All right, great. That's good. I didn't know that that's the way it worked. So you're good. I guess. If it says I tell you what, send me a text mail or send me a message in Web Courses and tell me, Dr. B, can you double check that I'm on the roster for this semester? Because I was on the roster for your astronomy a couple of semesters ago. And then I'll know to look. Okay? So get your iClicker out and be ready to click here in a few minutes. Notation. There's a notation that we use in physics, the delta, Greek letter delta, capital delta. And frequently we use these symbols delta t and delta x and delta other stuff as well. Delta t comes from the idea of an elapsed time. If you're figuring out an elapsed time, which is what your stopwatch does, it basically starts it and stops it and displays the difference of the two times. That's how you figure out an elapsed time. So it's a difference in the time coordinates between two different events. You know, you start running and you stop running. You're like Usain Bolt running a 100-meter sprint in 9-point-something seconds. If you're standing by and you're looking at your wristwatch, it might say 2:21 and 13 seconds when he starts, 2:21 in the afternoon and 13 seconds, and then 2:21, 22 point something when he finishes and crosses the finish line. So that's what I mean by two different time readings. And the notation that we use for that is instead of writing difference, we use Greek letter delta, capital Greek letter delta. So delta t means later minus earlier, t2 minus t1. So the later time is t2, the earlier time is t1. And this is always, in terms of delta t, this is always a positive number. Delta x means a change in position or a displacement. And here's an example. Go ahead and make a sketch of x1 and then x2 on the x-axis. I kind of sloped it up, slanted it up at for perspective. But if you're going from point x1 to point x2, all on the x-axis, that's really good. You can figure out the distance pretty easily. Just take the difference between x2 and x1. Because if in this sense, we're looking at bigger x coordinates to the right. So x2 is going to be a bigger number, like 7.3, and x1 is going to be a little bit smaller, like 4.2. And so the difference of those is the distance that you travel. Okay, so difference in x coordinates, the notation that we use for that is delta x, and that's x2 minus x1. And that's later position minus earlier position. Usually that's the connotation. Now it's possible for delta x to be negative if you're moving to the left. Okay, so if you go to if you start at negative 3.1 and you go to negative 6.1, okay, you've gone deeper into the negatives, your displacement is actually, delta x is actually negative 3. And but it would work out exactly the same, x2 minus x1. All right, so that's the delta notation that we're going to be using. It's usually later minus earlier, second minus first, etc., etc. Okay, and so the speed that we compute for a pair of measurements is based on delta x and delta t. Specifically, the formula for speed is delta x divided by delta t. All right, so if you look at the speedometer on your car, it says miles per hour. Distance divided by time. Distance in miles divided by elapsed time in hours. Okay, so if you go 60 miles in 1 hour, your average speed for that 1 hour is 60 mph. All right. Now, I'm going to give you a, make sure you have this formula ready. We're going to be using it with clicking and stuff for a few minutes. Let's take a look at a skateboarder's measurements, or the measurements of position of a skateboarder going down the aisle. All right. And we actually have these distance measurements, 3.58, 7.16, 10.74. 10.74, young lady with the glasses here, could you raise your hand? This young lady here is about 10.74 meters from the very top where the aisle starts to slant. Caitlin and Jordan, were you up on the level part when you started? Pretty much? Okay. But right close to where it started to slope, right? Yeah, okay. So right where it starts to slope is about 10.74 meters back from where this young lady's standing. What's your first name? Amber. Question? Yeah, where Amber's, so she's about 10.74 meters along. And these are actual real times that we measured last semester. And, you know, if we'd done time measurements for Caitlin and Jordan, you know, we might have come up with something different or something very similar to this. Okay, so T, A, J, and M, those are actually the initials of the students sitting along that side. But last semester we had a huge class, about double the size of this one, and so it was people all the way in the back of the room. Anyway, go ahead and copy this data down, and let's just look through it. Time T is, that was a guy named Tyler in the back row, and he was the starter. He started everything. Time T equals 0, position 0. That's where the origin of the x-axis was for our skateboard experiment. And then here's the time measurement for one of the skateboarders. At 1.82, the skateboarder passed this position, 3.58. Now that was about 4 rows down, as I recall. And then another 4 rows down, and notice this is twice as far, 7.16. And then this is another 3.5 above that. Okay. So another 4 rows down, I think it was, at this position, 7.16. So, yo, with the gray sweater, yeah, that's you. Yeah. What's your first name? Jonathan. Raise your hand real high. Where Jonathan was, that's about where 7.16 is. And if 3.58 is a little bit, you know, uphill from him. About back where the 7th row is, I guess. Or the 8th row, maybe. So at 3.16 seconds, ding, this is where they were, 7.16. And then down here at Amber's position, it took them 4.28 seconds to get to this position. So this is a set of times and positions. And hey, you guys, to get a velocity, you need at least 2 of these rows. Okay, you need, you know, the T row and the A row, or the A row and the J row. Or you could go from the T row all the way to the M row. You figure out an average velocity for the entire motion. Okay, so you can figure out any of the average velocities that you like. Now, we know that the skateboarder is speeding up here, and you can kind of see it because look, the time it takes to go from 3.58 to 7.16. What is that anyways? That's like 1.34 seconds from here to here. And then this one is 1.12 seconds to go the same distance. So this skateboarder definitely is speeding up, and you can see it in these specs. All right, let's figure out from this the average speed, V. All right, and we're going to go, first one we're going to do is initial point T down to point A. So that's up here to here. And we're going to figure out delta t and delta x for the interval whose endpoint is event A, passing by the student up there at 3.58 meters from the top. And then we're going to do on Clicker the average speed between point A and point J. So we're going to figure out delta t and delta x for this row down here. Okay, so make sure you have some room there to jot in some calculations. And then I think for homework, we're going to do this row down here, right? So, and that'll be for homework between J and M. Now, let's get down to business. Delta t is simple, t2 minus t1. Okay, t later minus t earlier is 1.82 minus 0. So go ahead and write down, for this one, delta t equals t2 minus t1, or t subscript a minus t subscript capital T, 1.82 seconds minus 0. And so delta t here is, this one's cinchy because one of the numbers is 0. Similarly, delta x is pretty cinchy because your final time, or your later time, 3.58, and your earlier position, 3.58 meters, and your earlier position is 0, right? And so this one's kind of cinchy, 3.58. Can you calculate, have you got your calculators out? Yeah, you better get them out. If you've got them. If you don't have them, you better start bringing them, because we'll use them pretty much every day, every Tuesday, every Thursday. Break out your calculator. iPhone is okay. What do you get for the ratio delta x divided by delta t? Raise your hand if you've got a value. Go ahead. Okay, I see that over there. You've got one? Okay, you've got one in red. Anybody over here got one yet? Wait. I was trying to remember your name, man. Trevor, right? Don Drysdale. Sandy Koufax. You're not even a pitcher. Okay. What's your first name? Luke. I was close. I would have gotten it. Okay, Luke, what do you got? Anybody verify that? 1.9? Raise your hand if you verify. 1.97. All right, good. All right, so 1.97. There we go. And hey, you guys, up here at the top, I have the units of measurement. Now, we're not doing miles per hour. We're doing meters per second. And just so you have a visual reference, what is a meter? A meter is about as, see this, what I'm up here? Yo, everybody look up here. Yo. Yeah, good. Everybody. All right. This is about a meter tall. This table where the document camera is, that's about a meter. And this lectern here is about 2 meters wide. So this is about this lectern, is that you could fit it into a box about 2 cubic meters. And this separate table over here with the doc cam is not quite a meter across, so maybe a little bit less than 1 cubic meter. Okay. So a meter per second is basically going this distance in 1 second, or a meter per second is going this distance here in 2 seconds. So that'd be a meter per second in speed. All right, you got this stuff down? Now, let's look at the next interval from A to J. What's the delta t from A to J? Go ahead and calculate that. So that's t subscript j minus t subscript a. T2 minus T1. Raise your hand if you got a value. I see you up in the front here. I see you back there. I see you over there. Anybody? What do you got? Is that what you have? 1.34? Okay, 1.34, good. I agree. Okay, so there's your delta t. And let's try a delta x. So this is x subscript j minus x subscript a. x2 minus x1. Who's got a figure for, okay, I see you in the very back row. Who else has got one? I see you over on the aisle, good. Okay. What have you got?
I got 3.58.
3.58, is that what you got? Okay, looks like we verify. All right, so make sure you have those written down in your table. All right, and now what we're going to do on iClicker to fill in the last box on that row, we're going to use iClicker 2. All right, so go ahead and do your calculation. Do it in your notes, and let me give you a multiple choice question. Oh, and by the way, we're on frequency BB. Bravo, bravo. For those of you without one, for the first time, hold the power button until it's flashing, and then type in the letters B and B again, and you'll get a little check mark, and it'll say go nitro, and that means you're good. And then you can, let's see, let's do this. Now you can start voting. And all you have to do is type in, just click the letter A, B, C, D, or E. These are multiple choice questions. And so you just gotta, it's looking for one click from you. Right? Eventually we'll be typing in numbers and letters, and then you have to hit the send button. But if it's just for a multiple choice, it's looking for, and hey, you guys, you can change your answer if you want. If you decide it's letter A instead of letter E, go ahead and do it. Change it. It remembers the first thing you type in and the last thing you type in. All right, 30 seconds to vote. And I have 125 answers so far. That's good. I'll be synchronizing the roster for this class right after class at lunchtime when I'm eating my lunch. And I'll give you bonus points if you're on the roster by lunchtime, by the time I sync. Yeah, so it'd be like noon or so. Question? No, you just have to click. Just type the letter A, B, C, D, or E. Question? What's that? To get the frequency, you hold the power button down, this kind of reddish button. Hold it down until it flashes a flashing square. Okay? And then type BB. Bravo, bravo. All right? All right. And then did you get Go Nitro? Yeah, all right. That's good. All right, let's stop. Way over. Raise your hand if you got it right. Dun, 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 dun. Good. Whoa. You guys are geniuses. Everybody, you guys did good. All right. If you're down there with B or C, yeah, it's just delta T or delta X over delta T for that particular interval. Now, I'm going to ask you some questions for homework, so make sure you have this data down. And the homework is going to be about these boxes down here. So a little bit of extra practice and some more, and I'll push you ahead into reading the entire rest of chapter 1. So the homework will force you to read. In other words, if we don't cover it in class today, you'll be able to catch it by reading, studying. Now, I have another question for you in just a second, but are there any questions about what we just did, the calculation we just did? Let me pause for that. Yes?
For the average, the meters per second, it's represented with the V.
Yeah. The question was, the average meters per second, the average speed, is that always represented with the symbol V? And the answer is yes. V is the traditional symbol for speed. And here's a side note, we haven't really done it yet, but if we care about the direction of it and want to write the velocity as a vector, we would write down the speed and then a comma and then the direction, like northeast or something. And then we would use a V with a little teeny arrow over the top of it. And we'll use that notation probably Thursday because it's important for us. Right now we're in one-dimensional motion, so the direction's set, we're not changing it. But Thursday we'll be thinking about 2 dimensions and more, so I'll bring that up. All right, another question. Now this one, you're going to have to really think about this. You may have noticed that skateboarder was not smoothly accelerating. In other words, he didn't get the same amount of meters per second for every second of motion, at least according to those measurements. Now let's think about a smoothly accelerating skateboarder. Read carefully and answer. Let me start the question for you. So this is like if we had a speed gun, Rebecca, down here at the bottom of the aisle. We could get a guy, time a guy at exactly 1 second, exactly 3 seconds. The actual speed at that instant. So 4 meters per second is not an average speed. Similarly, 8 meters per second is not an average. It's the instantaneous. If you have a radar gun, you're pretty much getting the instantaneous speed. In other words, the actual speed at that time. So what is the... okay, 20 seconds to vote. And I predict we're going to have answers all over the place. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let me stop this. And let's look at the, and it looks like we've got a good scatter here, or a significant scatter in the answers. A lot of people are voting for D, which is 6 meters per second, but a bunch of you are voting for 12, 8, and 4. Now, which one is the correct? Well, to do an average, what do? You add up how many of you've got, and then you divide by that number. So we've got 2 speeds divided by 2. And so therefore the answer to that is 6. Okay, 12 divided by 2. And many of you voted for that, and that's great. 65%. That's pretty good. And is there a question? Anybody want a question to reinforce? Okay, let me ask you another question. And this one is going to be a real brain burner. Think carefully about this one. Here's a graph of speed on the vertical axis and time down here. And this is a graph of the smooth skateboarder. started at 4 meters per second at 1.00 seconds, and then at time 3 seconds, he was up here at 8 meters per second. Just this same data here. But now I've got it expressed as a speed versus time graph. All right? So the question is, what is the instantaneous speed at what time is the instantaneous speed equal to the average? And you should write this particular question down in your notes because it is significant. At what time is the instant? See, this graph here on a speed versus time graph, the instantaneous speed is where the line is. Okay? The average speed is not represented here. It's computed from the data here, but the average speed is not represented here. Only the instantaneous. So at every time in motion, you put a dot. And when you put all the dots in, you have this dotted line here, or a solid line if you have enough dots. Okay? So what will the time coordinate be when the instantaneous speed, and you can read it right off this chart, if you think, if you're good at interpreting data. 30 seconds to vote. And make sure to jot this question down into your notes because, it, as I said, it is significant. It's that there's actually a principle behind this, not just a cool calculation. This is an example of a significant principle for us. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys got here. Whoa. You guys are geniuses. This is a smart class. That's nice. Good. I'm glad. Yeah, 2.0 seconds is the correct answer. And here's the dot. Go ahead and add this to your notes. There it is, right there. Right up here. 6 across from 6 and above 2.0. And if it's smoothly accelerating, first of all, the graph is a straight line. It's not curved. It's not flat. It's sloped up at a given angle. Second, if it's smoothly accelerating, the average is exactly halfway between the two end times, the initial and the final time. Let me repeat that. That's the general principle here. For smooth acceleration, the instantaneous speed equals the average speed halfway through the interval. Okay, at time t equals, 3 plus 1 divided by 2. The halfway time is when the instantaneous speed is equal to the average speed. Okay? So there's the general principle. Instantaneous speed equals the average at the halfway time. In this case, 3 plus 1 divided by 2, that's the halfway. That's the midpoint between those two times. Now, for the next few minutes before we dismiss, I see you guys putting on your coats. We're going to go all the way to 3:50, I think, today. So I don't think we'll be dismissing early. So don't put your coats on yet. All right. Now, I want to check out another graph of speed. All right. And go ahead and write down this equation of motion. Delta V equals A delta T. And in this equation of motion, we will be able to figure out changes in speed from changes in time, elapsed time, if we know this constant A, this quantity A. And that quantity A is going to be, for us, the acceleration. All right, so let's figure this out. And what we're going to do is start with a really, really cinchy graph. But it's important. And this one is constant speed. So go ahead and make a graph, a velocity graph, and go positive and negative on the velocity side. So now, what is your first name again? Yeah, Alana. Now, Alana, we've actually got a velocity graph because plus means forward, -1 down here means backwards or leftward. Okay, so now we can distinguish directions on this graph. So it properly is called a velocity graph. So let's say that we have an object that's just going along at 1 meter per second. You know, and walking for most people is 4 or 5 meters per second. 2 meters per second is just kind of poking along. So this is ultra pokey. They're just going along 1 meter per second. You know, they're listening to their iTunes and they're blazing away on Facebook. So they're kind of oblivious. They're only doing 1 meter per second. Everybody else is kind of walking around them, you know. And they're doing it for 2.5 seconds. Now, the distance, think about this. You're going 1 meter per second, and you're doing it for 2.5 seconds, as in this graph. How far do you go? 2.5 seconds, 1 meter per second. You go 2.5 meters. And so the area, base times height, is the same as the distance. All right, now, seconds, so here's base times height. The area of this rectangle is base times height. Here's the base, 2.5 seconds. And here's the height, 1 meters per second. And the seconds here cancels the per second over here. And hey, you guys, this is delta t here, 2.5 seconds. That's the elapsed time at which this guy was moving. And here's the speed, and there's no what do you call it? There's no variation here, just 1 meter per second. And so the area computes out to the distance that you travel. And so for this particular velocity graph, it is kosher to interpret that green area over here between the graph itself, the dotted line, and the t-axis, that area, and then vertical lines left and right, if necessary. It's kosher to interpret that area as the distance traveled. And so this is a baby example, real simple, of a what we call a distance polygon. Go ahead and write that down. Distance polygon. And this is a 4-sided polygon. It's a rectangle. This is the distance rectangle for an object in constant, an object with constant velocity. So the distance, d, is equal to v times delta t. Distance equals speed times time, or elapsed time in our notation. All right? And it's based on the interpretation, or we're basing our equation on the interpretation of this particular velocity graph. Now, one side comment for you about this velocity graph. My side comment is, it is an abstract graph. So make a note, abstract. You can't see velocity. If we had regular XY graph paper, you know, X on the horizontal and Y on the vertical, and you sketched in the line, you could do, you could lay a meter stick or a rope or something like on the floor of this room or out in the hallway to represent that line segment. You can't do it here. This is abstract. You can't really, we don't have meter sticks specifically or measuring stick of any kind for speeds or velocities. We have to derive them from position measurements and time measurements. Okay, so it's an abstract graph. And now we're going to do a slightly different graph, okay, for something that's slowing down. Now, this particular diagram here that I have is, I want you to think of this as a strobe photo. And you know how if you're looking at, say, a hummingbird or a baseball or somebody throws, or like there's famous pictures of cats falling, they start upside down. And did you ever notice that? A cat always lands with its feet on the ground, supposedly. And they've taken strobe photos of that, in labs. You got to be a pretty big nerd to do that. But somebody has done that and published pictures. And it's just, they flash the strobe, the flash bulb, like every 1/10 of a second on the way down. Or in this case, every 1/10 of a second as it moves to the right. And as you can see, every 1/10 of a second, it covers less ground. All right, so there's the initial point over there at point A. Then the second point is point B, point C, D, and E. And each time interval is the same, but the distance intervals are not. So delta T, if you're going to build a table for this, hey, that's a good idea for homework. You'll have homework tonight by supper time, hopefully, if not sooner. I might do a homework assignment based on this diagram. So for this one, delta T is going to be 0.1 second for each level of my table, but the delta X's are going to be different. They're going to get smaller. It's slowing down. And so make a note. Here's a strobe diagram for something slowing down. Now the velocity triangle for this, it would look like this. Okay, say you start at 3 meters per second at time t equals 0, but then by the time you're down here at time t equals 4 seconds, you've stopped. You've come to a stop. Now that red dashed line is your velocity graph. The polygon below that and above the time axis with maybe 1 or 2 vertical lines left and right, and we have one on the left, that polygon we can interpret as the distance. This is called the distance triangle. All right? And it will represent for us the distance that something travels when it accelerates. My wonderful students, the slope of this line is the acceleration. Remember that from high school, rise over run? The slope is equal to rise over run, delta y over delta x. Well, here it's delta v over delta t. So go ahead and write down basic definition. I should have it on the slide, but I don't. Sorry about that. Basic definition of acceleration, delta v over delta t. A equals delta v over delta t. All right. And the equation of motion I mentioned a few minutes ago was a version of that same. Delta v equals a times delta t. In this case, the slope, okay, who remembers? Sloping down to the right, is this a positive slope or negative slope? Negatory. All right, so that means when you have a negative slope on your velocity graph, your acceleration number is negative. I mean, it's slowing you down. You're losing speed for every second of acceleration. Now, the area of a triangle is kind of cinchy. 1/2 base times height. Everybody knows that. Okay, that's geometry class, probably 7th grade math class even. I think that's when I learned it. Of course, you guys now, you learn stuff a lot earlier than I did. You might have learned that in 5th grade. Did you know I had like D minuses in math from 5th grade all the way to like 9th grade? But it's true. And in 10th grade, I just started to light it up because it was geometry class, so it was all visual. If you haven't figured this out, I'm a visual thinker and I express things visually, and everything I do is diagrams first, at least diagrams first, and then notes. And geometry is where I just start to light it up. Plus, the geometry teacher was really cute. And anyway, base is 4 seconds for the triangle, and the height is 3 meters per second. All right? And so now I'm going to move this factor of 1/2, and I'm going to put it underneath that 3 meters per second. All right, so here it is. I just kind of rearrange it a little bit. Okay? And I'm going to leave you with this question. And maybe I'll give you a question about this on homework, because it's about time to dismiss. What is that quantity, 3 meters per second divided by 2? I'll leave you with that. You'll have some homework tonight, hopefully by supper time, if not sooner. Homework 3. Homework 1 will be extended if you're concerned about that. You're dismissed. I'll see you on Thursday. Thank you for clicking.